So for a while now, I've wanted to see if I can control lighting and camera settings in tandem together using a custom script. It could be really useful, and with the right camera API, you could control focus and f-stop and ISO and all sorts of camera settings depending on the lighting in your scene. And since it's almost Halloween, I figured I would do this with a spooky scene. So this is my jack-o'-lantern scene with ISO, f-stop, and white balance being controlled with lighting in a little diorama. In this video, I'm going to summarize how I accomplished this effect. For this project, I used a camera called the Zcam E1. I've mentioned it previously on the channel. It's a very special camera because of its size and its capabilities. What I am doing with it in this project is controlling the camera settings using HTTP requests. So since the camera has onboard Wi-Fi, we can connect to it like a normal Wi-Fi network using our Raspberry Pi and send HTTP requests to the camera, and depending on what string we request, we can change certain settings. So think of this as accessing multiple web pages on the camera, but they're not really web pages. We're just sending requests to those URLs, and then the camera is changing settings based on the requests that it receives. Here is a camera view where I've turned on the on-screen display, so you can actually see the values being changed as the video progresses. On the top, you see F followed by a number. That is the camera f-stop. You can see it's changing between 3.5 and 18. In the middle is the camera's ISO setting. That's changing between 10,000 and 400. And on the far right, you'll see a number followed by the letter K. That stands for Kelvin. That's actually the color temperature, or the white balance in this case. Now, there are four main lights in the scene. One of them is a fill light. It's just an LED off to the side. Then two of them are red automotive LEDs. One of them is inside the jack-o'-lantern. One of them is off to the side on the left. And then the last thing that I consider to be a light is that strip of RGB LEDs. With ISO and f-stop, primarily what we're doing is we're setting the f-stop to 3.5 and the ISO to 400 when the exterior automotive light is on. So during this stage, we want our scene to look brighter, so we're opening the aperture wider and we're decreasing the ISO because we don't need a higher ISO to compensate because we're letting a lot of light in. Then when that automotive LED turns off and the one inside the jack-o'-lantern turns on, we want it to look more intense, like a silhouette of a jack-o'-lantern face. So we turn the f-stop up to 18 and we turn the ISO up to 10,000 to compensate for the lack of light that we're getting because we've now closed our aperture a lot more. And ISO in a camera is basically the signal gain of our camera sensor. So we're turning up the sensitivity of the electronic sensor inside of our camera. And this creates a grainy, less saturated image, and we can see that silhouette of the face much more clearly. Also, when we increase the f-stop to 18, that allows for a wider depth of field. So you'll notice at f3.5, when the exterior light is on, more things are out of focus because our depth of field is shallow. And then when the LED inside the jack-o'-lantern is on, f18 comes into play, and that gives us a wider depth of field, so more things are in focus. Then the white balance. The values are rubber banding from 2300 Kelvin to something like 7500 Kelvin at intervals of 100 Kelvin. Those values are being changed based on the intensity of the RGB LEDs. When the LEDs are brighter, the scene becomes warmer. And when the LEDs are dimmer, the scene becomes colder. So it is these two lighting systems that we're using to influence the settings of our camera. So to make the pumpkin, I started in Blender. I created an SVG out of a jack-o'-lantern face using Adobe Illustrator, imported it into Blender, and then used it as the Boolean object. So I cut the face out. Here we are in Cura. That's the slicing program I used to create a G-code for the 3D printer. I set it to print very, very quickly. This was a very quick turnaround, so the results aren't the best, but essentially I used a solidify modifier in Blender, so I'm only printing the outer shell of the jack-o'-lantern, and you can see what it looks like there completed. Pretty decent. There are a lot of uneven ridges in it, but it's good for our purposes. Then I had to fit the jack-o'-lantern with an automotive LED that's going to be on the inside, and it's going to be used the lighting inside of our face. You can see me with the finished circuitry there that I already completed, hot gluing that LED into place in a little groove in the bottom part of the jack-o'-lantern, and then I hot glued the top part of the jack-o'-lantern on. And this was done very quickly. It doesn't have to be perfect, of course. I then used Woodland Scenic's foam putty to cover that seam, and later I painted it with some simple orange acrylic paint, and I hot glued it into position on our diorama that's already in place. So here we are at our setup. As you can see, the subject of our photo is in the center of this diorama that I had already set up. And you can see the lighting is changing distinctly between two different options. That we have a white LED off to the side. We have a fog machine. The automotive LEDs, one is off to the side right here. The other one is inside of our jack-o'-lantern. Our electronics setup. This is how we're controlling all of this lighting. Right in front of our diorama, we have the Zcam. That white balance value is also changing. The f-stop is switching between f3.5 and f18. Here is our Raspberry Pi. This is the brains of the entire system. It's how we are able to actually run two different scripts to control the lighting. Since the Raspberry Pi has onboard Wi-Fi, we've actually connected to the Wi-Fi of our Zcam these two cables. On the left, a UDMX cable, and on the right is a USB cable that goes to a relay module. We'll follow the blue cable first to the relay module. This relay module is controlling two circuits. Think of a relay module like a switch. It's essentially switching two different lights on and off. When one switch is on, the other one switches off. These are the automotive LEDs that we mentioned earlier. The UDMX module leads to this DMX decoder. The UDMX cable terminates in a DMX jack, which connects to our DMX controller. And right here you can see a pin out where we actually take that signal, split it into RGB channels, and connect that directly into our RGB LEDs. We have two scripts running on the Raspberry Pi. To ensure some high bitrate results, we're running the Zcam through a HDMI capture card. This way we don't have to rely on the onboard encoding of the Zcam. So just a fair warning, now I'm gonna jump into the programming side of things, and this part can get a little bit boring. It's not the most interesting. If you're interested in seeing what the programming actually was to get this done, go ahead and keep watching, but just to let you know that it gets a little bit monotonous. Oh, and the audio is not that great. Okay, so here we are in our Raspberry Pi. You'll notice on the top right, you can see the Wi-Fi is connected to Zcam Eagle 11 or Zcam Eagle 1. That's, of course, our camera. So we're connected to the Wi-Fi of our camera. And running ifconfig shows us our IP address. Now, here's an example of using an HTTP request to actually get information from our Zcam. Our camera IP address is 10.98.32.1 because the camera kind of acts as a wireless router. And this particular string fetches us the ISO value. It actually gives us the value, and it also gives all possible values of the ISO. So now we know which values our camera can have. Now, this string is how we can set our ISO. We can type in 3200 into our URL string, 3200, enter. Now the Zcam is set to 3200. So of our two scripts that control our lighting, let's start with LED flicker. This is for the automotive LEDs. So this is a bash script. I started off by setting 4 variables. One f-stop value for when the light in the pumpkin is off, and one f-stop value for when the LED in the pumpkin is on, one ISO value for when it's off, and one ISO value for when it's on. Then I create an infinite loop by saying while true, do. These first two commands, wget, are just sending the provided HTTP requests. The URL takes on the same form as what we typed into our browser, except we're using those variables. Then we use a program called crelay to turn relay 4 on and relay 3 off. So in this case, relay 4 is our pumpkin LED, and relay 3 is the outer LED. So we're turning the pumpkin LED on, so we're actually setting those settings that we talked about, and then setting the LEDs on and off respectively. The whole point of the repetitiveness of this script is that I can actually set specific sleep times. The sleep time is just a delay. So here we're waiting for 0.3 seconds. Each time we come back from the sleep, we're actually setting the opposite settings. So here we're turning relay 4 off and relay 3 on. Then we're setting the pumpkin off ISO and the pumpkin off f-stop. So we're switching everything. Obviously, there are easier ways to do this. If we wanted it to be completely random, we could have it so that it selects a random number and then sleeps for that amount of time and then runs the secondary commands, and then I could just have a loop of those two sets. In this case, I wanted more control over how long it's sleeping each time. Done right here ends our infinite loop. For our second script, RGB Pulse, this is the one controlling the RGB LEDs. I downloaded a program called UDMX Linux, and basically what this does is it allows us to send channel numbers to our UDMX USB dongle, and then that goes to the DMX controller. I set a variable called incrementer. I set a reverse Boolean variable, meaning is it going in reverse, and then the white balance value, which will constantly be changing. The idea here is that we're counting up to 255 and then down again to 60. The maximum value in an RGB lighting setup is 255, and the lowest is 0, but we don't want it to go all the way to 0, so we set the lowest to 60.
If incrementer is greater than 253, then reverse equals 1. If it's less than 60, then reverse equals 0. So basically, when we get down to 60, we start counting up. When we get up to 253, we start counting down. This is where that is honored. If reverse is 1, that means that we're subtracting 3 each time. If reverse equals 0, that means we're adding 3 each time. That's how we are able to control which direction the lighting is going, and each time it adds 3 or subtracts 3 RGB values from the green channel and the red channel to make orange.
So here's where things get a little crazy. Our lowest possible white balance is 2300, our highest possible is 7500. Our lowest possible RGB value in this case is 60, and our highest is 255. How do we find out which white balance we should send the camera for which RGB value? Depending on how you do it, you want to find the slope of the line and the y-intercept. This is y-intercept form. If you remember from school, y equals mx plus b. M is the slope, of course, x is the x value, and b is that y-intercept. We'll say x is our white balance and y is our RGB value. Once you find the slope and everything, you find that our formula is y equals 0.0375x minus 26.25. Once you get that down into terms of x, you get this. So to find x, we would add 26.25 to it and then divide that value by 0.0375, and that would give us x, which is our white balance, and that's what we would send the camera. Well, in a bash script, we can't actually use float values, so we have to use whole numbers. So instead of adding 26.25, we round down to 26. That's what we're doing here. White balance equals incrementer plus 26, so RGB plus 26. Then instead of dividing by 0.0375, if we do 1 divided by 0.0375, we get roughly 27, multiplying by 27 instead of dividing by 0.0375. Then, to round it to the nearest 100, we use this little formula. We divide it by 100, then multiply it by 100. When this gets run, it basically rounds it to 100. And this is because we can only set white balance values in increments of 100 because of the Zcam. Since we rounded that value to 26, there are some errors. Sometimes it goes below 2300 because we rounded. So this is a failsafe. If it goes less than 2300, then we set it back to 2300. And the same for 7500. If it goes over the maximum, we set it back to the maximum.
Once all of that is done, we set the camera white balance to the white balance value that we just calculated. We used the UDMX utility that we downloaded and set channels 1 and 2 to that incrementer value. So we're changing the green value and the red value by the same amount.
So although there were flaws with this project, for example the painting of the pumpkin and things like that, it wasn't perfect, but this was a giant experiment and I think it turned out pretty interesting. So let me know if you'd like to see more of this type of content, or maybe a mix of coding and visual effects in the future. I would like to integrate programming into a lot of my content in the future, and if you enjoy this type of video or other videos I've produced, go ahead and subscribe. And happy Halloween!